Okay, using the logistic growth model. Now, logistic growth model is f of x, which is equal to c divided by 1 plus a e to negative bx, where c over 1 plus a is the initial value, c is the carrying capacity or limiting value, and b is a constant determined by the rate of growth. Now, for example 6, an influenza epidemic spreads throughout a population rapidly at a rate that depends on two factors. The more people who have the flu, the more rapidly it spreads. And also, the more uninfected people there are, the more rapidly it spreads. These two factors make the logistic model a good one to study the spread of communicable diseases. And clearly, there is a maximum value for the number of people infected, which is the entire population. Now, for example, at time is equal to 0, or the initial time, there is one person in a community of 1,000 people who has the flu. So in that community, at most, 1,000 people can have the flu. Researchers find that for this particular strain of the flu, the logistic growth constant is B, which is equal to 0.6030. And we're going to estimate the number of people in this community who will have had this flu after 10 days. So let's predict how many people in this community will have had this flu after a long period of time has passed. So the first thing we want to do is we want to substitute the given data into the logistic growth model. So there's our logistic growth model. Now, because at most 1,000 people, the entire population of the community, can get the flu, then we know the limiting value is C, which is equal to 1,000. So in order to find A, we need to use the formula that the number of cases at time t is equal to 0, which in this case, we're going to call it x. So time represents x, which at 0. So f of 0 where t is equal to 0, there is one person in the community. So that's how we have the input as 0, the output is 1. And then we know that C is going to equal 100. So if we plug it into this formula, there is our output, which is 1. There is our value of C. And then we know that there's the value of 0. So now, in order for us to solve, we know that anything to the power of 0 is going to be 1. So e to the 0 in this scenario is going to be 1. So we have 1, which is equal to 100 over 1 plus a. And now our goal is to solve for a. In order to do that, we're going to multiply both sides by the quantity 1 plus a. So multiplying both sides by the quantity of 1 plus a leaves us with 1 times 1 plus a, which is equal to 1,000. Distributing that 1 just leaves us with the same as a plus 1, which is equal to 1,000. Subtracting 1 to both sides, now we know that a is going to equal 999. Now in step 3, now we can fill in our model that we have from step number 1. We know that C represents 1,000. We figured out now that a is going to equal 999. And we also know that the constant b, which is equal to negative 0.6030. So now here is our formula. Now what this model does, it predicts that after 10 days, the number of people who have had the flu is going to be the following. So we need to represent t to be 10 and plug it into our function. So f of 10 is going to equal 1,000 divided by 1 plus 99 times e to the power of negative 0.6030 times 10, and that's going to approximately give us 293.8. So because the actual number must be a whole number, a person has either had the flu or not, we're going to round to 294. So in the long term, the number of people who will contract the flu is a limiting value C is equal to 1,000. Now remember that because we are dealing with a virus, we cannot predict with certainty the number of people infected. The model only approximates the number of people infected and will not give us exact or actual values. The graph that you can see here in figure 7 gives a good picture of how this model fits the data. So here is day 1. Day 1, you have 1 case on day 0. And then on day 5, it increases to 20. On day 10, you get 294. And then according to the population within that community, eventually it's going to level off at that equilibrium point. In this scenario, which is y equals 1,000.